A massive stone block sits before you, polished to a mirror finish. This level of precision should not exist in the ancient world, yet it does. This is the stone-cutting paradox, a mystery that defies our entire timeline of human progress. By the end of our journey, you will see the ancient world not as a primitive beginning, but as a chapter filled with forgotten genius. We will explore how builders in Egypt shaped granite with impossible accuracy, and how walls in Peru were assembled like a cosmic jigsaw puzzle. What does it mean when the physical evidence of the past contradicts the history we think we know? The story we have been taught is one of steady, linear advancement. Our textbooks describe a clear path from stone to bronze to iron, a timeline where each new material unlocks greater possibilities. In this familiar narrative, the ancient Egyptians, the Inca, and other early builders worked with simple tools of copper, bronze, and stone. They were masters of leverage and manpower, yes, but bound by the physical limits of their era. This is the foundation upon which our understanding of history rests. Yet, standing before the evidence, this foundation begins to crack. The paradox emerges not from a lack of skill, but from an apparent surplus of capability. How do you explain the cutting of granite, one of the hardest stones on Earth, with a precision measured in the thickness of a human hair, using tools supposedly made of softer metals? This is not a question of effort, but of method. It suggests techniques that, according to our established timeline, simply should not have existed. Archaeologists who work hands-on with these monuments are the first to acknowledge the gap. Dr. Mark Lehner, who has spent decades excavating and mapping the Giza Plateau, has stated plainly that while we understand the broad strokes of pyramid construction, the exact methods for achieving such flawless stonework remain, in his words, educated guesses. This admission is crucial. It highlights a quiet but profound debate within the field. We see the finished product, but the blueprint for the process itself seems to have been lost. The paradox forces a difficult question. Have we, in our modern arrogance, fundamentally underestimated the scope of ancient engineering ingenuity? What if the progression of knowledge is not a straight line forever ascending, but a cycle where peaks of understanding can be reached, forgotten, and then stumbled upon again millennia later? This matters because it reshapes our view of human potential. If these cultures possessed and then lost advanced stoneworking techniques, it means our history is not merely a record of accumulation, but also one of subtraction. Great libraries can burn, empires can fall, and entire schools of practical knowledge can vanish into the sand, leaving behind only their indestructible monuments as silent, puzzling testimonials. To solve this stone-cutting paradox, we must look closer, moving from the broad question to a specific, tangible enigma. We begin with a site where the stones themselves seem to defy the very laws of physics, a place where the walls are not built but woven. High in the sun-baked quarries of southern Egypt, a story of interrupted ambition is written in stone. Here lies the unfinished obelisk, a colossal finger of red granite that would have been the largest ever erected, had it not cracked during its extraction from the bedrock. It is a frozen moment, a snapshot of ancient engineering in progress, and its surface tells a tale that contradicts our simplest assumptions. The tool marks left behind are not the shallow, ragged gouges one might expect from pounding soft copper chisels into one of the hardest stones on the planet. Instead, they are clean, deliberate channels. To work granite, which sits near the top of the mineral hardness scale, requires something far more persistent than brute force. Modern geologists and engineers who study these marks point to a necessary combination: abrasives and tools with a durability that pushes against the boundaries of the historical record. The accepted theory is that workers used a slurry of sand, a quartz abrasive harder than the granite itself, mixed with water, and dragged it back and forth with copper saws or drills. This makes logical sense, yet the scale and speed implied by the quarried stone present a lingering puzzle. Using such a method to free an 1,100-ton obelisk is akin to trying to cut down a giant redwood tree with a piece of dental floss. It is technically possible, but the efficiency required for such monumental projects strains belief. This mystery of method deepens when we examine the finished products. Consider the original casing stones of the Great Pyramid, blocks of fine white limestone that once sheathed the structure, reflecting the desert sun. Though most are gone, a few remain at the base, and the joints between them are not merely good, they are flawless. The fit is so precise that the gap is often thinner than a sheet of paper with no visible mortar. A modern razor blade cannot slip between them. Achieving this is not just a matter of careful carving. It speaks to a mastery of measurement, leveling, and surface finishing that seems to belong to a much later age of technology. How did they transform rough, quarried blocks into faces this perfectly flat? How did they ensure that each block, weighing many tons, matched its neighbor with such hair's breadth accuracy across an entire monumental surface? The anomaly in Egypt is not one of effort but of execution. It presents a clear paradox: the tools and materials we believe they had versus the immaculate, enduring results they undeniably achieved. This single sight compels us to widen our gaze, for if such precision was possible in the sands of Egypt, could it have been replicated in other corners of the ancient world, perhaps using a completely different approach to the same impossible problem? Across the ocean, another answer to the stone-cutting paradox rises from the mountains of Peru. The fortress of Sacsayhuamán, perched high above the Inca capital of Cusco, is a masterpiece of defensive architecture. Its most famous feature is a series of 3 zigzagging walls, built from limestone blocks so enormous they seem borrowed from the realm of giants. Some stones weigh over 100 tons, yet they are fitted together in a mesmerizing, irregular jigsaw puzzle. What makes these walls a true anomaly is not just their size but their incredible resilience. For centuries, they have withstood powerful earthquakes that have leveled later Spanish colonial structures built right beside them. While the city below crumbled, these ancient walls simply settled and then settled back, their intricate joints absorbing and dispersing the seismic energy. This is not accidental durability, it is engineering of a profound order. The secret lies in the joints themselves. Look closely, and you see that the stones are not flat slabs stacked atop one another. Instead, each massive block has multiple faces, each carved with subtle, complex angles. Where one stone bulges outward in a convex curve, its neighbor is carved with a perfectly matching concave hollow. This creates a 3-dimensional lock, a bond so tight that, again, not even a razor blade can penetrate the seam. This polygonal masonry suggests a level of planning and execution that staggers the mind. How did the builders, without modern drafting software or precision instruments, visualize and then carve these intricate, complementary shapes across hundreds of disparate stones? Researcher Jean-Pierre Protzen spent years attempting to replicate Inca stonework using tools and methods documented from the era. He demonstrated how hammerstones could be used to pound and shape granite, and how sand abrasion could smooth surfaces. Yet, even after his practical experiments, Protzen openly acknowledged that certain aspects of the finest Inca joinery remained, in his words, elusive. The process of achieving such perfect matches between irregular blocks, especially on their hidden interior faces, defies a complete explanation through the simple tools we have evidence for. The mystery deepens when we consider logistics. These limestone blocks were quarried from sites several kilometers away, across steep and rugged terrain. The Inca had no wheeled carts, no draft animals larger than llamas, and no iron tools. The transportation of a single 100-ton block up and down mountain paths represents a monumental feat of communal labor, rope technology, and engineering cleverness that we can only partially reconstruct. So we are left with a reflective question: does the perfection of Sacsayhuamán point to a lost technical method, a specific trick of the trade that vanished with the empire? Or does it reveal a deeper cultural knowledge, a philosophy where building was not just construction, but a sacred act of weaving the very landscape itself into a unified, unshakable whole? This pattern of impossible precision is not confined to one civilization. As we move from the mountains of Peru, we find the same signature of mastery etched into the bedrock of a different continent, in a place where the stones were not merely moved but seemingly melted. The scale of ambition shifts from intricate puzzles to raw, overwhelming mass at the ancient site of Baalbek. Here, in the Bekaa Valley of Lebanon, rests the foundation of the Roman Temple of Jupiter, and upon it sits the Trilithon, a platform of 3 limestone blocks whose dimensions defy belief. Each stone is estimated to weigh over 800 tons, the equivalent of 2 fully loaded jumbo jets. They are positioned nearly 20 feet above the ground, fitted together with a precision that mocks their impossible weight. Even with our most powerful modern cranes and hydraulic systems, moving and placing a single block of this scale would be a monumental engineering challenge, requiring meticulous planning and specialized equipment. The paradox here is one of logistics on a staggering scale. How did builders, whether Roman or perhaps inheriting an even older tradition, not only quarry these behemoths but also transport them over half a mile from the quarry and then lift them into perfect position? Contemporary engineers who have studied the site propose methods based on known ancient technology, a system of wooden rollers, enormous levers, and vast teams of laborers and oxen pulling on ropes. The mathematics suggest it is possible, but the margin for error is vanishingly small. A single slip, a snapped rope, or a cracked roller would mean catastrophe. The flawless execution we see implies not just possibility, but a repeatable, mastered process. The cutting techniques add another layer of mystery. The surfaces of these megaliths are smoothly dressed, their joints tight and clean, showing few of the dramatic tool marks one might expect from such a Herculean task. This suggests a final stage of finishing that is almost delicate, a contrast to the brutal force required for their movement. Not far from the temple complex lies the quarry, home to an even larger monolith known as the Stone of the Pregnant Woman. This block, still partially attached to the bedrock, weighs an estimated 1,000 tons. It is a snapshot of the quarrying process, showing how channels were cut around it, likely by teams of workers driving wooden wedges into pre-cut slots and then soaking them with water to expand the wood and fracture the stone. Yet, freeing the block is only the first step. The true enigma begins the moment it is separated from the earth. Moving it requires a level of social organization that is itself a form of advanced technology. Coordinating thousands of workers, feeding and housing them, managing the supply of ropes, wood, and tools, and executing a complex, multi-stage maneuver over weeks or months. This points to a societal sophistication that transcends simple manual labor. It represents a collective will and a logistical genius that challenges our modern perception of ancient capabilities. The silent stones of Baalbek compel us to ask, did these cultures possess a specific, now lost toolkit of engineering principles, or was their true secret an unparalleled mastery of human coordination and applied physics, a knowledge so complete it allowed them to treat mountains as clay? To find a potential answer, we must shift our focus from the stones themselves to the hands that shaped them and the subtle traces they left behind. The gap between the tools we have found and the work they supposedly accomplished forms the very heart of the paradox. To understand this, we can listen to the experiences of modern stonemasons who have attempted to bridge this gap with their own hands. Skilled artisans using meticulously recreated copper chisels and stone hammers have tried to replicate the fine finishes seen on Egyptian granite or the complex joints of Inca walls. Time and again, they report a frustrating disconnect. While they can shape the stone, achieving that signature ancient precision, especially on hard igneous rock like granite or basalt, is a painstakingly slow process that often falls short of the original's flawless quality. The tools work, but they do not seem to work well enough or fast enough to explain the monumental scale we see. This practical experience points to a missing piece in our historical toolkit. The archaeological record shows us tools made of copper and bronze. These metals were the height of technology for millennia, yet from a materials science perspective, they have a fundamental limitation. Copper is relatively soft. Bronze, an alloy of copper and tin, is harder and holds an edge better, but both are still significantly softer than quartz, the mineral that gives granite its hardness. Imagine trying to carve a brick using only a stick of butter. The butter will deform long before the brick does. This is the core of the tool Enigma. To cut granite, you need something harder than the granite itself. This is why the abrasive theory is so central to mainstream archaeology. The idea is that the ancient craftsmen used the material's own weakness against it. By using a slurry of wet sand which contains tiny, sharp quartz crystals and dragging a soft copper saw or drill tube through it, the quartz does the actual cutting. The copper is merely a vehicle to deliver the abrasive. This method is undeniably effective, and experiments have proven it can produce clean cuts. Teams like those from the Nova television series have demonstrated this process, showing how a copper tube driven by a bow drill, fed with sand and water, can slowly bore a hole into granite. The result is a core that perfectly matches examples found in ancient Egyptian quarries. The evidence seems conclusive, and yet a nagging question of scale remains. These experiments also reveal the agonizing slowness of the technique. To quarry, shape, and finish the thousands of tons of stone in a major pyramid using only these methods would require timelines and labor forces that push the boundaries of historical plausibility. Other methods, like pounding granite with even harder stones like dolerite, are possible but are brutally inefficient, producing vast amounts of rubble for a small amount of shaped stone. This leads materials scientists and engineers to quietly speculate about other possibilities. Could the ancients have discovered and utilized even harder abrasives? Diamond dust, for instance, or certain rare minerals would dramatically increase cutting speed. There is, however, a profound silence in the record. No direct evidence, no workshop residue, no textual reference definitively points to the systematic use of such materials. Some researchers point to the sheer polish achievable on statues and vessels, a luster so deep it seems liquid, and wonder if a lost polishing compound or technique was involved. The tool Enigma, therefore, is not simply about what they used, but about the staggering efficiency with which they must have used it. We see the simple tools, and we can make them work, but we cannot make them work fast enough to match the historical footprint. This forces a subtle but critical shift in the investigation. If the tools themselves do not fully explain the outcome, then we must look even closer, beyond the method of cutting, to the guiding intelligence behind it. How did they know exactly where to cut? This brings us to the silent language of the stones themselves, a language of angles, lines, and measurements of impossible accuracy. The true depth of the ancient stone-cutting paradox is not fully visible to the naked eye. It is a secret whispered in millimeters, a story told by the tiniest deviations from perfect flatness and alignment. To understand it, we must compare these works not to other ancient monuments, but to the products of our own most precise industries. Imagine a modern machine shop where components are milled to tolerances finer than a human hair, where surfaces are ground so flat that they can be used as reference planes. This is the realm of precision engineering, a world of lasers, digital readouts, and computer-controlled tools. Astonishingly, when we apply these same laser scanners and photogrammetric surveys to the oldest stoneworks on Earth, they often meet this modern standard. The surfaces of granite boxes in the Serapeum of Saqqara, for instance, show a flatness across their entire length that is measurable in fractions of a millimeter. The corners are not just roughly square, they are precise to within tiny angular deviations. This level of accuracy is not merely impressive craftsmanship, it is a technological statement. It implies a deep working knowledge of geometry, of plane geometry, and of three-dimensional spatial reasoning that our history books rarely attribute to these eras. Perhaps most compellingly, it suggests the possible use of a standardized, repeatable unit of measurement, a master template of perfection against which every stone was checked. Researchers like engineer Christopher Dunn have spent decades analyzing this precision. He argues that the tool marks and geometries seen in Egypt, particularly inside the Great Pyramid and on granite artifacts, are not just the result of hand tools but bear the hallmarks of machinery. He points to the harmonic, consistent feed marks on cut surfaces that suggest a rotating tool applying even, sustained pressure, something far beyond a simple handheld bow drill. The question he raises is provocative. Could the ancients have developed a form of advanced machining, using tools powered not by electricity, but by water, weight, or some other mechanical advantage we have yet to rediscover? The mainstream explanation for achieving such flatness revolves around the mastery of basic principles taken to an extreme. The method of grinding with a slurry of abrasive sand and water, using a large, flat stone as a sanding plate, is perfectly capable of creating a flawless surface. Similarly, the use of a simple straight edge, a length of wood or stone with a true edge, combined with a skilled eye and a patience we can scarcely comprehend, could guide the final finishing. The mystery is not whether these methods work, but how they were applied with such unwavering consistency across vast projects. Consider the base of the Great Pyramid. Its four sides are not just roughly aligned to the cardinal directions, they are nearly perfect in their orientation. The lengths of the sides are so closely matched that the difference between the longest and shortest is less than the width of your hand, forming a square of staggering accuracy over an area covering more than 13 acres. This was not achieved by eyeballing it. It required a system of measurement, alignment, and verification that functioned perfectly from one corner of the massive site to the other, year after year. This brings us to a quiet, reflective crossroads in our investigation. Does this millimeter-perfect world demand that we accept the existence of lost high technology, of tools and machines that have left no physical trace in the archaeological record? Or does it force us to radically redefine the upper limits of human skill, patience, and sensory acuity? Could a culture, through generations of dedicated practice, develop a tactile and visual sense so refined that the hand could feel deviations the eye could not see, achieving through relentless iteration what we achieve with digital calibration? This focus on vibration and resonance, on the subtle frequencies that pass through stone, may hold a key to the final, most elusive piece of the puzzle. Legends from across the world whisper of a different kind of tool, one that left no mark in the stone but may have resonated in the air. In the high Himalayas, Tibetan monks speak of ancient texts describing acoustic levitation, where the chanting of specific tones could lift massive blocks. In the Americas, some indigenous stories tell of ancestors who used sacred songs to coax stones into place. These are not isolated tales, they form a persistent, global motif that suggests a forgotten relationship between sound and matter. This leads us to the sonic hypothesis, a speculative but deeply intriguing corner of the stone-cutting paradox. Could the ancients have used directed sound or vibration to soften granite, to make it temporarily malleable, or to reduce the immense friction during transport? While firmly in the realm of alternative history, the idea is not pure fantasy. It is grounded in observable physics. Researcher John Reed, inspired by these legends, conducted experiments with sonic generators. He focused intense sound waves at samples of granite and observed a curious effect. The surface of the stone appeared to become less brittle, almost putty-like, under specific resonant frequencies. The scientific principle at play is resonance, the same phenomenon that allows an opera singer to shatter a wine glass. Every object has a natural frequency at which it vibrates most easily. If you can match that frequency with an external sound or vibration, you transfer energy into the material with incredible efficiency. For a crystalline structure like granite, this sustained internal vibration could theoretically cause microscopic fatigue, loosening the bonds between mineral grains and effectively making the stone easier to work. It could also create a layer of agitated particles at the surface, reducing the friction between a cutting tool and the stone itself, allowing a copper saw to glide through with far less effort. The physics, while complex, is sound. The problem, as always, is evidence. No ancient sonic devices have been unearthed. No clear depictions of such technology exist in hieroglyphs or pottery. Yet, some modern explorers report strange acoustic phenomena at ancient sites. There are accounts of certain chambers within pyramids or temples where sound behaves unusually, where a whisper can be heard clearly across a room, or where a specific note seems to hum through the stone itself. Are these intentional acoustic effects or mere coincidences of architecture? This is where we must tread carefully between tantalizing possibility and historical fact. The sonic hypothesis forces a profound question. Are these widespread legends merely poetic metaphors for communal effort, or could they be distant, garbled memories of a genuine applied science, a physics of vibration that was lost when the last masters of the technique fell silent? While we may never find a sonic saw, the very persistence of the myth highlights a human intuition that there must have been something more, a missing catalyst that explains the impossible ease of these ancient works. If sound remains an unproven theory, it points our investigation toward other, more tangible forms of unseen assistance, perhaps not in the air but in the chemistry of the stone itself. Spanish chroniclers in the 16th century, traveling through the newly conquered Inca Empire, recorded a story that seemed more fantasy than fact. They wrote of local legends describing how the stones for their great fortresses were not cut and hauled, but were softened with a special plant juice, molded into place like clay, and then allowed to harden back into solid rock. To the European mind, this was impossible, a tall tale. Yet, this persistent story points us toward a radical and practical possibility. What if the ancient stone-cutting paradox was solved not with harder tools, but with a kind of lost alchemy, a chemistry that made the stone itself temporarily cooperative? This is the chemical softening theory, a hypothesis that suggests builders might have used natural compounds to etch, weaken, or even plasticize stone surfaces, turning an agonizing process of abrasion into a more manageable task of shaping. The idea is rooted in observable chemistry. Certain natural substances do react with stone. Take limestone, the primary building block of many ancient wonders. Chemists have demonstrated that organic acids, like oxalic acid found in rhubarb and sorrel plants, or citric acid from fruits, can slowly etch a calcium carbonate surface. Applied as a paste or a gel, such a substance could potentially soften the very top layer of the stone, allowing craftsmen to work it more easily before the acid was neutralized and washed away. Other researchers have pointed to silica-dissolving compounds. Some plants, like the Equisetum genus, also known as horsetail, contain high levels of silicic acid. In theory, a concentrated extract could interact with the silica bonds in granite, possibly making the crystalline matrix less resistant. The process would not be a magical melting, but a controlled surface degradation, turning solid rock into a material that could be scraped, shaped, or polished with far less physical effort. We can break down how such a technique might have worked in practice. First, the sourcing. Ancient cultures were master botanists with a deep, intimate knowledge of their local flora for medicine, poison, and ritual. Identifying plants with high acid content would have been within their realm of possibility. Second, the preparation. Creating a potent extract would involve harvesting, crushing, boiling, and reducing plant matter into a thick sap or a paste, a technology no more complex than making dyes or medicines. Third, the application. Workers could paint this compound onto a stone surface or pack it into a pre-scored cut line, allowing it to dwell and react. Finally, the working. While the surface was in this altered state, using even simple copper or stone tools could carve it efficiently. Once the desired shape was achieved, rainwater or a deliberate washing would halt the reaction, leaving behind a perfectly shaped, chemically etched stone that would then fuse seamlessly with its neighbor over time through natural pressure and mineralization. A compelling, though mysterious, parallel exists far from Peru in the vitrified stone forts of Scotland. These Iron Age hill forts, like Tap O' Noth, have sections of their stone walls that appear to have been fused together by intense heat, creating a glassy, slag-like material. Archaeologists have long debated the cause. Was it the result of a catastrophic siege fire so hot it melted granite, or was it intentional, a method of strengthening the ramparts? Some experiments suggest that combining certain mineral-rich rocks with organic material and then setting a fire could generate enough heat to cause vitrification. This phenomenon shows that the interaction between heat, chemistry, and stone can produce dramatic, lasting changes. While not the same as chemical softening, it reinforces a broader principle. Ancient builders may have understood and harnessed transformative processes that we are only beginning to recognize. So, could this explain the seamless joints of Sacsayhuamán or the mirror finishes in Egypt? It is a tantalizing thought. If you could temporarily soften the mating surfaces of two irregular stones, you could press them together, allowing them to conform to each other's shapes under pressure before they rehardened. This would create that signature, airtight fit. Yet, for all its elegant logic, the chemical theory faces a significant hurdle, a profound lack of direct evidence. No ancient recipes for stone softening compounds have been found in any tomb or temple archive. No residue analysis of tool marks or joint surfaces has conclusively identified such chemicals. The stories recorded by the Spanish are just that, stories, passed down through generations and filtered through the lens of conquest and wonder. They could be metaphorical, describing the almost supernatural skill of the masons, rather than a literal technical manual. This leaves us at a fascinating crossroads of interpretation. Does the absence of proof mean it never happened? Or does it simply mean that the knowledge was so practical, so guarded, that it was never written down, and its organic tools, the plants and the pastes, returned to the earth without a trace? The chemical angle, whether ultimately proven or not, forces a crucial shift in our perspective. It moves the mystery from the realm of impossible force to the realm of clever catalysis. It suggests that the true genius may not have been in moving mountains, but in subtly persuading them to move themselves. This focus on unseen assistance, whether chemical or acoustic, inevitably leads us to the final, and perhaps most humbling, piece of the puzzle: the sheer human endeavor required to orchestrate such projects, and what the drive to build them reveals about the civilizations that did. The moment a stone is separated from the quarry floor, an even greater challenge begins. It must travel. Imagine a single block from Sacsayhuamán, a 100-ton mass of limestone, needing to journey several kilometers up a mountain path. The Inca had no wheels, no carts, and no animals stronger than a llama to pull it. This is the transportation paradox, a logistical puzzle that rivals the cutting mystery in its sheer impossibility. How do you move the unmovable? The answer lies not in a single magical trick, but in a symphony of simple physics, meticulous planning, and raw human coordination on a scale that stuns the modern mind. Historians and engineers like Egyptologist Bob Brier have spent years reconstructing these ancient feats of movement. The most widely accepted method involves a combination of sledges, rollers, and prepared pathways. A massive wooden sledge would be constructed beneath the stone. To get it moving, teams would place rounded logs acting as rollers in front of the sledge. As the sledge moved forward, workers behind would rush to retrieve the rollers that had passed underneath and carry them to the front, creating a continuous, rolling road. The key to making this work was defeating friction. Experiments show that dragging a heavy sledge directly on sand or dirt requires an immense, almost impossible amount of force. But pour water onto the path ahead and something remarkable happens. The wet sand or clay creates a slick, plastic surface that dramatically reduces friction. A famous Egyptian tomb painting from the Middle Kingdom actually depicts this exact scene. A colossal statue being pulled on a sledge by a large team of workers, with a figure standing at the front pouring liquid onto the pathway. This simple act of lubrication transforms an impossible drag into a manageable, albeit still Herculean, pull. The coordination required was itself a form of advanced engineering. Moving a multi-ton block required a conductor's precision. Teams of pullers, sometimes numbering in the hundreds, had to haul in unison, guided by rhythmic chanting or drum beats to synchronize their efforts. Other teams were dedicated to the constant work of moving the wooden rollers, while still others prepared the route ahead, leveling ground, building ramps, and managing the crucial water supply. This was not a chaotic mob, it was a disciplined, hierarchical machine. The organizational structure needed to feed, house, and direct this temporary army of laborers for months or years points to a social sophistication that we often overlook when marveling at the stones alone. These principles of logistics were applied in astonishingly diverse environments. Far from the mountains of Peru, the Olmec civilization of ancient Mexico faced its own transport nightmare. They carved colossal heads, some weighing over 20 tons, from solid basalt boulders sourced from distant mountains. These heads then had to be transported over 60 miles through dense, swampy jungle and across rivers to their ceremonial centers. Without beasts of burden, the Olmec likely used a combination of log rollers and rafts, maneuvering these immense portraits of their rulers through a landscape that actively fought against them. An even more isolated mystery unfolds on Easter Island. The iconic moai, those silent sentinel statues, were carved from volcanic rock at an inland quarry. Somehow, hundreds of them were moved miles across the island to stone platforms along the coast. Local oral tradition speaks of the statues walking, guided by spiritual power. Modern experiments have shown that a walking motion, with teams using ropes to sway the statue from side to side while pulling it forward, is a surprisingly viable method. Whether this was the actual ancient technique remains unknown, but it highlights a universal truth. Each culture engineered a solution tailored to its unique environment and resources. This leads to a reflective question about the societies that undertook these tasks. What kind of collective will, what shared belief or unified purpose could motivate thousands of people to dedicate years of their lives to such backbreaking, monotonous labor? The answer may lie not just in the earthly realm of engineering, but in the celestial one. The movement of these stones was always directed, always purposeful, leading to a specific, sacred location. And often, that final placement was dictated by something far above the ground, by the precise movements of the sun, moon, and stars. The stones were placed not just on the earth, but in conversation with the sky. From the lonely Salisbury Plain in England to the sun-baked banks of the Nile in Egypt, the grandest stone monuments of antiquity share a curious trait: their alignments are not random. They are precise celestial instruments, oriented to capture the first light of the solstice sun or to frame the rise of a significant star. This astronomical precision is the final, and perhaps most profound, layer of the stone-cutting paradox. It suggests that the flawless joinery and the impossible logistics were not ends in themselves, but means to a cosmic purpose. The same cultures that mastered the millimeter were also mapping the movements of the heavens. Consider Stonehenge, that iconic ring of Sarsen stones. For centuries, it was seen as a mysterious temple. Then, in the 1960s, an astronomer named Gerald Hawkins used an early computer to analyze its layout. He discovered that the arrangement of the stones created dozens of alignments with key solar and lunar events, like the summer solstice sunrise and the winter solstice sunset. Hawkins proposed that Stonehenge could have been used as a sophisticated calendar, a stone computer for predicting eclipses and marking the seasons. His work was controversial, but it fundamentally shifted our understanding. These structures were not just built, they were engineered to track time on a celestial scale. This level of intentionality required more than just stacking rocks. It demanded a deep, observational science. So how did ancient builders without telescopes or written star charts achieve such accurate alignments? The methods were elegantly simple, rooted in patient observation of shadows and horizons. One likely tool was the gnomon, a simple vertical pole. By tracking the path of its shadow throughout the day and across the year, a surveyor could map the sun's journey, identifying the longest and shortest shadows that mark the solstices. Water levels, using the principle that water seeks its own level, could establish perfectly flat plains over long distances for foundational layouts. The real genius was in transferring these celestial observations to the ground with unwavering accuracy. This was a multi-generational project of watching, marking, and remembering. At a site like the Temple of Karnak in Egypt, the axis of the entire complex is aligned to the winter solstice sunrise. To achieve this, priests and architects would have observed the sun's position on that sacred day, year after year, planting markers on the distant horizon. The construction of the temple's massive pylons and columns then had to follow that invisible line with absolute fidelity, a task requiring the same geometric precision seen in their stone cutting. This connection between the cosmic and the terrestrial is made stunningly clear at a much older, quieter site. In the Egyptian desert west of the Nile lies Nabta Playa, a stone circle dating back over 7,000 years. It is one of the world's oldest known astronomical observatories. Here, smaller stones were arranged to align with the rising points of key stars, particularly those of the constellation Orion. This was a calendar carved into the desert floor, used by nomadic cattle herders to predict the coming of the seasonal rains. Nabta Playa proves that the drive to understand and codify the heavens predates pyramids and empires. It is a foundational human impulse. This brings us to a pivotal question. Did this celestial drive actually fuel the need for such precise stonework? The answer seems to be yes. If your goal is to create a permanent marker for a solar event that occurs once a year, your construction must be exact. A doorway aligned to the solstice sunrise is only meaningful if the edges of that doorway are straight and true, if the entire structure is perfectly oriented. A slight error in the flatness of a surface or the angle of a wall would mean the sun's ray would not strike the intended target, rendering the sacred geometry useless. The astronomical purpose did not just inspire monumental construction, it demanded the highest possible engineering standards. The stone-cutting techniques and the celestial alignments are two sides of the same coin, both born from a desire to create permanent, flawless expressions of an understood cosmic order. This hints at a unified knowledge system where the priest, the astronomer, and the master mason were often the same person, or parts of a tightly integrated tradition. The legacy of this cosmic connection is what truly challenges our linear view of progress. It suggests that these ancient cultures possessed an integrated wisdom, a holistic understanding that wove together precise material science with profound spiritual cosmology. They built not just to impress but to commune, using the most durable material on Earth to capture the most fleeting light from the sky. The scattered stones of our planet tell a curious story, one that repeats itself across vast oceans and unconnected continents. From the polygonal walls of Peru to the granite boxes of Egypt, from the ziggurats of Mesopotamia to the silent moai of Easter Island, we find the same signature of impossible precision. These civilizations, according to the mainstream historical record, never met. They shared no letters, no trade routes, no maps, yet they arrived at staggeringly similar solutions to the same monumental problem: how to make stone obey the human will. This is the paradox of parallel innovation, and it forces a fundamental question about the nature of human discovery. Did this knowledge arise independently in isolated pockets of genius, or does it point to a thread of connection we have yet to find? This debate has divided researchers for over a century, forming two broad schools of thought. On one side is the idea of independent invention. This perspective, favored by many modern anthropologists, holds that human beings, when faced with similar environmental challenges and material limitations, will naturally converge on similar technological solutions. It is a testament to the universal ingenuity of the human mind. If you need to move a heavy stone, you will likely invent the lever and the roller. If you need to cut it, you will discover the power of abrasives. The pyramid form, seen in both Egypt and Mesoamerica, is arguably the most stable way to build tall with stone, a shape that gravity itself suggests. The differences within this similarity are telling. The smooth-sided, limestone-cased pyramids of Giza were primarily tombs, central to a complex funerary religion focused on the pharaoh's celestial journey. The stepped pyramids of Teotihuacan or Chichen Itza were temples, platforms for ritual and sacrifice, often topped with ornate sanctuaries. Their functions were culturally distinct, even if their foundational geometry echoed a common structural logic. On the other side of the debate stands diffusionism, the idea that complex technologies spread from a single source, carried by migrating peoples or long-forgotten voyages. Its most famous modern proponent was the adventurer Thor Heyerdahl. He famously argued that transoceanic contact was not only possible but probable. To prove his point, he built the Kon-Tiki, a balsa-wood raft based on ancient Peruvian designs, and sailed it from South America to Polynesia in 1947. His voyage demonstrated that such journeys were feasible with prehistoric technology. Heyerdahl believed that cultural parallels, like pyramid building or specific stone working techniques, were not coincidences but evidence of such ancient contact. He once stated, "Borders, I have never seen one, but I have heard they exist in the minds of some people." His work challenged the academic isolationist model, forcing a reconsideration of just how interconnected the ancient world might have been. When we look closer at specific techniques, the parallels become even more intriguing. Consider the corbelled arch, a structure where each successive layer of stone projects slightly inward until the gap is bridged at the top. This ingenious method for creating doorways and roofs without a true keystone arch appears in the tombs of Mycenaean Greece, the temples of the Maya, and the storehouses of the Inca. It is a logical solution to spanning a space with stone, but its widespread, independent emergence still gives pause. Even more striking is the polygonal masonry we explored earlier. The intricate jigsaw puzzle walls of Sacsayhuamán find a distant cousin in the polygonal foundations of some Mycenaean walls in Greece, and even in certain ancient constructions in Japan. The technique is so specific, so labor-intensive, that its repeated invention seems less likely. Could it be that this method represents a peak solution, a kind of ultimate answer to building earthquake-resistant, enduring structures that different cultures discovered when they pushed stoneworking to its absolute limit. This global tapestry of stone leads us to a profound crossroads of interpretation. Does this pattern suggest a lost global civilization, a single advanced source from which all others sprang, as some alternative historians propose? The evidence for such a cataclysmically forgotten worldwide culture remains speculative, lacking the clear archaeological trail demanded by mainstream science. The more widely accepted, yet equally awe-inspiring, conclusion is that it demonstrates the incredible, innate capacity of the human mind. Faced with the same raw materials of rock, gravity, and time, disparate cultures, driven by their own unique spiritual and practical needs, climbed the same mountain of innovation and arrived at similar vistas. It speaks not to a single lost teacher, but to a shared, hardwired potential for genius. This potential, however, required a catalyst to turn potential into reality, to shape stone with such finesse. These cultures all needed one essential, humble partner. Their greatest works were not just feats of engineering, but also triumphs of hydrology, for every cut, every polish began with the simple, vital element of water. The same element that carved the Grand Canyon over eons could have been harnessed as a precision tool. Water, under immense pressure, is a relentless sculptor of stone, and ancient engineers were masters of its flow. While we marvel at aqueducts delivering water to cities, we must consider a more active role. Could hydraulic power have been the silent partner in the stone-cutting paradox, providing the consistent force needed for tasks that seem impossible with muscle alone? The principle is straightforward. When water is forced through a narrow opening, its velocity and cutting power increase dramatically. This is the same natural process that creates smooth, curved channels in riverbeds over centuries. The leap from observing this to intentionally applying it is where ancient ingenuity enters. Civilizations like the Minoans on Crete, over 3,000 years ago, built sophisticated underground clay pipes and pressure systems that could direct water with surprising force, demonstrating a clear understanding of hydraulics. Applying this knowledge to stonework is a logical, though elusive, possibility. One compelling application is in quarrying itself. Imagine a scenario where workers first cut a narrow channel into the bedrock around a desired block. Then, instead of laboriously hammering wooden wedges, they direct a sustained, high-pressure stream of water, perhaps enhanced with abrasive sand, into that channel. The jet would erode the stone at the fracture line, steadily deepening the cut and efficiently separating the block with clean edges. This method would require a significant and controlled water supply, but for cultures that built extensive irrigation networks, managing such a resource was a core skill. Evidence that hints at this approach exists at sites like Tiwanaku in Bolivia. Here, around the ancient quarries, archaeologists have identified complex networks of canals and channels. While their primary purpose was likely irrigation and drainage, their proximity to the stone sources is provocative. Could these waterworks have had a dual function, serving also as the delivery system for hydraulic quarrying tools? The transport of these quarried stones presents another arena where water was almost certainly a key player. Moving a multi-ton block over land is one challenge, floating it is another. Engineers studying sites like the pyramids have long proposed that an extensive network of canals, fed by the annual Nile flood, was used to bring stones directly to the construction site. A block loaded onto a barge becomes almost weightless, gliding on water with a fraction of the effort needed for land transport. This isn't just speculation. Sediment cores near the Giza Plateau have revealed traces of what appear to be ancient, now silted waterways. The combination is powerful: hydraulic force to aid in extraction and hydraulic buoyancy to enable movement. So, does the presence of advanced water management solve the paradox? It provides an elegant, physically plausible piece of the puzzle. Water power could explain the clean cuts, the efficient quarrying, and the logistics of moving megaliths. It represents a form of simple machine, amplifying human effort through clever application of natural physics. Yet, like the other theories, direct archaeological proof of pressurized cutting jets remains just out of reach. No ancient hose nozzles or pump mechanisms have been found in a stonemason's workshop. This brings our investigation to a pivotal point. We have explored the potential of tools, abrasives, chemistry, sound, and hydraulics. Each offers a plausible fragment of the answer, but perhaps the true secret was not in a single lost technology, but in the synthesis of them all, guided by a mind of extraordinary skill. Behind every impossible stone lies the hand of a master we will never know. These were not slaves driven by a whip, as outdated narratives once claimed, but highly skilled artisans, members of what we might call secret guilds, who dedicated their entire lives to a single, monumental craft. Their names are lost to history, but their legacy is etched in granite. Their expertise was not stored in libraries, but in muscle memory and keen eyesight, passed from teacher to apprentice over generations. This was the realm of tacit knowledge, a form of understanding so deeply ingrained through practice that it defies written explanation. Historian Lynn Meskel notes that in ancient Egypt, craftsmen lived in dedicated villages like Deir el-Medina, where skills in stoneworking, painting, and sculpture were hereditary trades. A father would teach his son not just how to hold a chisel, but how to listen to the stone, to feel the difference in resistance between granite and limestone, to judge the perfect consistency of an abrasive slurry by its sound and texture. This knowledge was transmitted through demonstration, correction, and years of repetitive, mindful practice. It was an oral and tactile tradition, as fragile as human memory. Within these closed communities, techniques were refined through relentless trial and error. A master mason might spend a decade experimenting with different quarrying angles or polishing compounds, slowly perfecting a method that would then become the guild's guarded secret. This incremental innovation, accumulated over centuries, could transform a crude technique into a high art. They developed specialized tools for specific tasks, not just generic chisels, but tools for undercutting, for creating concave surfaces, for achieving a final polish so fine it captured light like glass. We can see a parallel, though with different materials, in the later medieval cathedral builders of Europe. These masons also operated in secretive guilds, using complex geometry and templates passed down through apprenticeships. They left behind few written manuals, but their soaring stone vaults speak of a profound, practiced understanding of load and stress. So we must ask, what irreplaceable secrets died with the last masters of the ancient world? What nuanced tricks for finding a stone's natural fracture line, or recipes for a forgotten polishing paste, vanished when their lineage was broken by war, famine, or cultural collapse? This loss of tacit knowledge is perhaps the most human element of the entire paradox. It suggests that the true technology was not in a tool, but in the cultivated intuition of the artisan. This deep, sensory understanding of material naturally extended into a mastery of form, guiding their hands to create the perfect angles and flawless planes that still mystify us today. A perfect spiral unfurls on a seashell. The same elegant curve appears in a hurricane viewed from space. This is sacred geometry, a hidden language of shapes and ratios that the ancients saw woven into the fabric of nature itself. They didn't just admire these patterns, they built them into the very bones of their monuments, turning stone into frozen mathematics. The beauty of a rose window or the floor plan of a temple is not merely decorative, it is a functional blueprint, a set of precise instructions that guided every cut, every alignment, and every proportion. This mathematical consciousness may be the most overlooked tool in the ancient builder's kit. Researchers like John Mitchell spent a lifetime exploring what he called the geometric code of ancient landscapes. He proposed that sites from Stonehenge to the Great Pyramid were positioned according to a vast, interconnected web of alignments and proportions, using numbers and shapes considered sacred across cultures. Whether one subscribes to his full theory or not, his work highlights an undeniable truth. These builders thought in shapes. They used geometry as a practical design language. The tools for this were astonishingly simple: a length of cord, a set of stakes, and a deep understanding of basic ratios. With a cord knotted at regular intervals, a surveyor could create a perfect right angle, the foundation of stable construction, by forming a triangle with sides in the ratio of 3, 4, and 5. This Pythagorean triangle, known millennia before the Greek philosopher gave it his name, was a carpenter's square etched into rope. Stretching cords between stakes driven into the earth, they could lay out the entire ground plan of a city or a temple, translating celestial alignments into terrestrial lines with flawless accuracy. The application of these principles produced structures that resonate with mathematical harmony. The Great Pyramid's base perimeter, when compared to its height, yields a ratio that is remarkably close to 2 pi, suggesting a symbolic representation of the circle's relationship to its radius. The interior chambers and passageways are positioned according to complex geometric schemes that continue to be studied and debated. Across the world, in the mandala-like layouts of Hindu temples like Angkor Wat, we see the same intentionality. These temples are conceived as microcosms of the universe, their towers and courtyards arranged in concentric squares and circles that map cosmic order onto the earth. This geometric rigor was not an abstract exercise, it was the engine of their precision. When every angle in your design is derived from a sacred triangle or a divine ratio, your cutting instructions become unambiguous. A mason tasked with dressing a stone for a specific corner didn't need complex written specs. He needed to know it was part of a 7, 11, 24 triangle, and his tools were set accordingly. The geometry dictated the cut, ensuring that every piece, once finished, would lock into its predetermined place in the grand design. This mathematical foundation connects directly to the very materials they chose. Why use granite for certain elements and limestone for others? Beyond durability, certain stones may have been selected for their crystalline structure, their ability to take a precise polish, or even their resonant properties, all factors that would serve the geometric and possibly harmonic function of the whole. The stones themselves became the physical pixels in a vast, three-dimensional geometric code. So, did this pervasive mathematical mindset enable their impossible precision? It provided the unwavering template, the perfect ideal against which all physical work was measured. But a perfect plan on the ground is one thing, executing it on a block of unforgiving granite is another. This leads us to consider the final, most personal dimension of the mystery, the human sensorium. Could the ultimate tool have been the cultivated sensitivity of the artisan's own body? The quarry floor is not just a source of stone, it is a library of materials. An ancient engineer walking through it would not see identical blocks, but a palette of possibilities, each with its own strengths and weaknesses. Their selection was the first, and perhaps most critical, step in solving the stone-cutting paradox, a decision rooted in a deep, intuitive understanding of material science. They knew that the right stone for a foundation was not the right stone for a statue, and their choices reveal a sophisticated knowledge of geology that we are only now fully appreciating through modern analysis. Geologists who examine these monuments don't just see architecture, they see a record of stress, compression, and environmental interaction written in the stone itself. By studying the wear patterns on obelisks or the weathering on temple walls, they can deduce the properties the builders were seeking. The primary criteria were clear. Hardness was paramount for enduring monuments meant to last for eternity. Granite and basalt, with their interlocking crystalline structures, resist crushing force and environmental erosion, making them ideal for load-bearing columns and outer casings that face the elements. Yet hardness comes with a cost. It makes the stone incredibly difficult to work. This is where grain size enters the equation. A fine-grained stone like some limestones or the granodiorite used for the Rosetta Stone offers a compromise. It is durable enough to withstand centuries, but its uniform, smaller crystals allow for more precise carving and polishing. The surface can be made smooth enough to hold the intricate, shallow inscriptions of a decree that needed to be copied and distributed across a kingdom, every hieroglyph, demotic script, and Greek letter remaining legible for millennia. Availability was the final, practical master. Even the most perfect stone was useless if it lay 1,000 miles away across impassable terrain. The proximity of the Aswan granite quarries to the Nile, which served as a liquid highway, made that immensely hard material a viable choice for Egypt's grandest projects. This interplay of property and purpose directly influenced the cutting techniques. The method for shaping relatively soft limestone with copper chisels would be useless against granite, necessitating the abrasive sand process or the speculative chemical or sonic methods we've discussed. The stone itself dictated the tool. This leads to a fascinating practical question. How did they test these materials without laboratories or hardness scales? The answer likely lies in generations of accumulated tactile experience. A master mason would learn by doing, by striking different outcrops with a hammerstone and listening to the ring, by feeling the grit under a polishing stone, by observing how different types weathered in the local climate over a lifetime. This was knowledge earned through trial and error, passed down as the most valuable trade secret of all. This meticulous selection process, however, points to something far greater than practical engineering. It underscores the profound societal intention behind these projects. A culture does not go through the immense trouble of quarrying, transporting, and flawlessly shaping a stone like granite for a temporary shelter or a mundane building. The choice of material signifies the intended permanence of the message or the function. When you build a tomb from a mountain, you are stating, in the most physical terms possible, that the memory of the person within is meant to be as eternal as the earth itself. When you carve a law into a slab of impervious granodiorite, you are declaring that the order it proclaims is unchangeable, anchored for all time. The stone was not just a building block, it was a statement of legacy. This drive to create a permanent legacy, to speak across centuries, brings us to the final, unifying force behind all these disparate mysteries, the profound human need for meaning that could compel entire civilizations to move mountains. A pharaoh surveys the desert from his palace, envisioning a mountain of stone that will bear his name for eternity. This was not mere vanity, but a foundational act of statecraft. The staggering scale and precision of ancient stonework were driven by forces far deeper than technical curiosity. They were the direct expression of a society's most vital beliefs and ambitions. Historian Yuval Noah Harari points to a crucial ingredient for such endeavors: a shared fiction. He argues that large-scale human cooperation, whether building pyramids or modern corporations, hinges on our unique ability to believe collectively in abstract ideas like divine kingship, national glory, or an afterlife. The stone itself became the physical anchor for those powerful, unifying stories. To understand the paradox of their methods, we must first grasp the immense cultural and political imperatives that made such a monumental investment not just possible, but essential. These projects served multiple, intertwined functions, each demanding permanence. First, as cosmic models, temples like the Parthenon in Greece or Angkor Wat in Cambodia were not just houses for gods, they were microcosms of the universe built to sacred geometric principles. Their perfect proportions and alignments were believed to maintain cosmic order, harmony between heaven and earth. A wall out of true or a column improperly aligned wasn't just poor craftsmanship, it was a spiritual failure that could disrupt the balance of the world. This sacred function created an uncompromising demand for precision. Second, as bridges to the afterlife. For the Egyptians, a tomb was a machine for resurrection. The pyramid's flawless geometry and airtight construction were designed to protect the pharaoh's physical remains and his spirit, ensuring his successful journey to join the gods. Any flaw in the stonework could be a crack in this cosmic vessel, jeopardizing eternity itself. The material had to be perfect because the stakes were literally infinite. Third, as assertions of power, a fortress like Sacsayhuamán with its unmovable walls was a statement in stone. It declared the Inca emperor's absolute authority over both his people and the very landscape. The impossible effort required to build it demonstrated the state's capacity to command thousands of lives, its logistical mastery proving its right to rule. The stone was both shield and symbol. So, did these profound purposes necessitate the extreme precision we marvel at today? Absolutely. When you are building for the gods for eternity or for absolute dominion, good enough is not an option. The cultural imperative created a technological imperative. There was no room for the margin of error allowed in everyday construction. The spiritual and political blueprint demanded a physical execution to match. This understanding of the why finally brings our investigation full circle, from mystery to method, and now to the ultimate test. If we comprehend the drivers, can we, with our modern knowledge, finally close the loop and recreate the how? This leads us directly to the workshops and experiments of today, where engineers and artisans are putting ancient claims to the proof. Theories are one thing, but stone does not lie. To truly test the paradox, we must move from speculation to action, from the library to the quarry floor. In recent decades, archaeologists and engineers have rolled up their sleeves to attempt what was once considered impossible, replicating ancient stoneworking and transport using only the materials and methods believed to be available at the time. These modern replication efforts are our closest link to the hands of the ancient masters, and their findings are as humbling as they are revealing. One of the most famous public experiments was the Nova Pyramid Challenge, where a team of Egyptologists and skilled workers attempted to build a small pyramid using ancient techniques. They quarried limestone blocks using stone dolerite pounders, a brutally slow process that produced a shocking amount of rubble for each usable block. They moved a 2-ton stone on a wooden sledge over a lubricated path, a task that required a coordinated team and demonstrated the critical importance of that simple trick with water. The project proved it could be done, but it also laid bare the monumental scale of the labor and time required, forcing a new appreciation for the organizational genius behind the original. Beyond television specials, dedicated researchers have spent lifetimes in pursuit of these lost skills. Archaeologist Denys Stocks devoted years to experimenting with replicated copper tools and abrasives. He focused on the mystery of drilling into hard stone, like the granite cores found in Egyptian workshops, using a copper tube driven by a bow drill, fed with wet sand abrasive. Stocks was able to bore into granite, producing a core and a hole that were virtually identical to ancient examples. His work provided powerful, tangible proof that the abrasive theory is not just plausible, it works. Yet, his meticulous records also revealed the hidden costs. The copper saws and drill tubes wore out at an astonishing rate, requiring constant repair and replacement. The abrasive slurry had to be managed carefully, and the process demanded relentless, patient effort. Success was measured in millimeters per hour. These experiments answer one question while raising another deeper one. They show us the how, but they also illuminate the staggering human price of that how. The paradox shifts from being about impossibility to being about scale and sustainability. How did ancient societies maintain the sheer industrial output of tools, abrasives, and food to support such slow, meticulous work for generations? Another fascinating test took place far from the desert in the forests of Japan. Inspired by the mysteries of Easter Island, a team of researchers led by archaeologists Terry Hunt and Carl Lipo attempted to solve the riddle of the Moai transport. Dismissing the traditional theory of log rolling, which would have deforested the island, they proposed a method inspired by local oral tradition that the statues walked. Using a concrete replica of a Moai and teams of people with ropes, they demonstrated that by rocking the statue from side to side, they could make it pivot forward in a controlled walking motion. The experiment was a success, moving the multi-ton replica hundreds of meters with a surprisingly small crew. This proved that a counterintuitive, even elegant, solution was not only feasible but highly efficient, aligning with the ecological and archaeological evidence of the island. It was a powerful reminder that our first assumptions about ancient logistics are often the most literal, and therefore sometimes the most wrong. So, where does this leave us? Do these rigorous experiments finally solve the stone-cutting paradox? In one sense, yes. They demonstrate that with the tools we know they had, with immense patience and clever physics, the great works of antiquity are technically achievable. The mystery of pure impossibility dissolves, but in another, more profound sense, the paradox only deepens. The experiments reveal a yawning gap between technical possibility and historical reality. They show us a path, but it is a path of almost unimaginable toil, coordination, and time. They prove what could be done, yet they make the fact that it was done on such a colossal scale all the more bewildering. This gap between our successful small-scale replications and the monumental legacy we see is where the true mystery now resides. It forces a quiet but inevitable question. If our modern recreations, with all our hindsight and planning, still struggle to match the pace and precision of the ancients, what crucial piece of their world are we still missing? This persistent gap in our understanding naturally prompts a broader look at the historical canvas itself, leading some to wonder if the timeline we have constructed is missing entire chapters of innovation and exchange. The timeline of human civilization we accept is a story written by the victors of time, by what survived. But what if the winners were not the first to play the game? This leads us to the most speculative edge of the stone-cutting paradox, the quiet suggestion that our historical record may be missing entire chapters. Some researchers argue that the precision we see is not an anomaly within our timeline, but evidence from outside of it, a remnant of a sophisticated culture that flourished and then vanished long before the rise of Egypt or Sumer, lost to a cataclysm or simply to the relentless erosion of millennia. This idea is controversial, often dismissed by mainstream archaeology, yet it persists as a powerful undercurrent in the discussion because it offers a direct, if radical, solution to the mystery. If the techniques seem too advanced for their era, perhaps they belong to a different era altogether. Proponents of this view, like author and journalist Graham Hancock, frame human history not as a straight line but as a cycle with forgotten peaks. Hancock suggests we are a species with amnesia, and that monuments like the Great Pyramid or the ruins at Tiwanaku are not early attempts but late inheritances. He argues that these sites are the work of a lost civilization with advanced knowledge, survivors of a global cataclysm perhaps linked to the end of the last ice age, who then seeded their wisdom among the emerging cultures of the ancient world. In his own words, he posits that history is not the slow, incremental climb we imagine, but rather the story of a great forgetting followed by a long, slow remembering. This perspective recasts the stone-cutting paradox not as a puzzle to be solved within our known history, but as a clue pointing to a history we have yet to fully acknowledge. The evidence cited for such a forgotten chapter is often fragmentary and hotly debated. It points to anomalies that sit uncomfortably within the standard model. There are the submerged structures like the Yonaguni Monument off the coast of Japan, a series of massive, terraced formations that some geologists argue bear the marks of human modification, though others see only natural sandstone fracturing. There are out-of-place artifacts, objects that display a level of technology incongruous with their supposed age, though many of these have been debunked or lack clear provenance. Perhaps most compelling are the mythological correlations. Flood myths are not just a biblical story, they appear in the lore of hundreds of cultures worldwide, from the Mesopotamian epic of Gilgamesh to the legends of the Maya. Could these be distant, garbled memories of a real geological event that reset the human story? A tangible anchor for rethinking our timeline comes not from a speculative underwater site, but from a dry hilltop in Turkey. Göbekli Tepe is a sprawling complex of carved stone pillars arranged in circles, some weighing over 15 tons, decorated with intricate reliefs of animals. The revolutionary fact is its age. Carbon dating places its construction at around 9,600 years before the Common Era, making it over 11,500 years old. This is thousands of years before the invention of pottery or settled agriculture, long before the wheel or writing. According to the traditional narrative, complex society, monumental architecture, and organized religion should not exist at this time. Yet there it is. Göbekli Tepe forces archaeology to rewrite the opening chapters of civilization. It proves that hunter-gatherers were capable of staggering communal effort and sophisticated symbolic expression. If this was possible, what else might have been possible in the deep past that we have simply not yet found? So, could a lost civilization explain the stone-cutting techniques? In one sense, it provides a neat answer. It suggests the knowledge was already mature, a pre-existing technology passed down or stumbled upon by later cultures. It turns the paradox into a legacy, yet this theory faces immense scientific skepticism, primarily because of a profound lack of direct evidence. Where are the cities of this progenitor culture? Where is their trash, their tools, their everyday lives? The archaeological record shows a clear, if complex, progression of technology. The jump from Göbekli Tepe's carved limestone to the finished granite of the pyramids spans millennia of observable development. While the alternative timeline is a captivating narrative that honors the mystery of these sites, it may also risk overlooking a more subtle and perhaps more human truth. The answer to the paradox might not lie in a single forgotten teacher, but in the incredible, cumulative power of simple, overlooked innovations repeated across generations. Archimedes once claimed that with a lever long enough and a place to stand, he could move the world. This is not just a boast, but a profound insight into the physics that powered the ancient world. Our search for lost technologies might overlook the most powerful force of all, the elegant application of simple mechanics. The lever, the inclined plane, the pulley, these were the true engines behind the impossible. With enough time, enough coordination, and a deep understanding of basic physics, the movement and placement of megaliths becomes not a paradox, but a predictable outcome of applied force. Physicists who have modeled these ancient tasks arrive at a consistent conclusion. The mechanical advantage provided by a long lever or a gently sloping ramp is immense. It transforms an impossible lift into a manageable pull. For example, to raise a stone block weighing several tons to the top of a pyramid using only ramps, the required force is not the full weight of the block. It is a fraction determined by the ramp's angle. A long, gradual ramp of packed earth and brick, lubricated with water or clay, would allow teams of workers to drag stones upward with a sustained, coordinated effort. The secret was not in overcoming the weight all at once, but in dividing the work over time and distance. We see this principle in action across different cultures. The Romans, masters of practical engineering, used complex systems of wooden cranes powered by treadmills and counterweights to lift heavy stones for their aqueducts and colosseums. These machines were sophisticated, but their core components were levers, ropes, and the rotational force of human or animal power. They amplified effort through clever gearing and balance. A similar ingenuity appears in the transport of the Easter Island moe. Recent experiments showed that a relatively small team, using ropes to rock a statue from side to side, could make it pivot forward in a controlled walking motion. This method uses the statue's own center of gravity as a pivot point, a living application of leverage that requires no wheels, no logs, just rhythm and physics. Consider the use of counterweights. In some proposed models for pyramid construction, a system of heavy stone weights on the opposite side of a pivot could help lift a block, reducing the human effort needed by a significant margin. The pivot point itself, a sturdy wooden or stone fulcrum, becomes the most critical piece of technology. It concentrates all the distributed force of ropes and labor into a single, upward motion. This is not high technology. It is the fundamental technology of the ancient world, refined through observation and relentless practice. So, does this simple physics solve the stone-cutting paradox? It certainly demystifies the logistics. The movement of massive stones becomes a problem of organization and calorie consumption, not of magical levitation. But it also raises a reflective question. Have we, in our modern age of hydraulics and combustion engines, fundamentally lost an intuitive sense for what sheer human ingenuity, multiplied by simple machines, can achieve? We look at an 800-ton block and see impossibility. An ancient engineer might have seen a long ramp, a series of levers, and the patient work of seasons. This return to fundamentals shifts our focus from what they might have lost to what they undeniably possessed, a granular, intimate knowledge of their environment. The next layer of understanding may not be in the tools they held, but in the very world they worked within. The landscape was not an obstacle to be conquered, but a partner in the work. Ancient builders possessed a deep, intimate dialogue with their environment, seeing in every climate and terrain not a limitation, but a set of tools waiting to be used. This environmental ingenuity represents a quiet, often overlooked layer of the stone-cutting paradox. The same natural forces that could destroy a structure over centuries were harnessed to build it in the first place. Consider the simple, transformative power of water in its different states. In colder climates, the expansion of freezing water becomes a precise quarrying tool. There is evidence that cultures, including the Inuit and some Norse builders, used this method. They would drill or carve a line of holes along a desired fracture line in bedrock, fill them with water, and plug them with wooden wedges. As night fell and temperatures dropped, the water would freeze. Ice expands with tremendous force, roughly 9% by volume, enough to steadily and cleanly split the stone along the predetermined seam. This technique required no metal harder than the rock, only an understanding of seasonal cycles and the patience to let nature do the heavy lifting. In desert environments, sand itself became a crucial component. Dragging a massive stone sledge directly on bedrock would create catastrophic friction, but laying down a path of dry, loose sand creates its own problems. The solution was often found in achieving the perfect consistency. By dampening the sand to a specific degree, workers could create a firm yet plastic surface that reduced drag dramatically. Experiments have shown that the right amount of moisture causes sand grains to form tiny water bridges, binding them just enough to support weight without sticking. This turns a desert floor into a temporary, low-friction highway, a perfect example of using the local material to solve a local problem. The timing of work was often dictated by the rhythms of the earth. Quarrying in certain seasons could offer distinct advantages. In regions with a wet season, limestone and sandstone can become slightly softer and easier to work when saturated with rainwater. Strategic quarrying during these periods would make the initial shaping and cutting less labor-intensive. Once extracted, the stone would harden again as it dried, regaining its full durability for construction. Similarly, river floods were not just events to be survived, they were opportunities to be engineered. In Egypt, the annual inundation of the Nile was the lifeblood of agriculture, but it was also the key to logistics. Canals were dug to extend the floodwaters right to the construction sites at the plateau's edge. Giant barges, buoyant on the raised water, could float multi-ton blocks directly to the base of the pyramid, turning a year-round land transport nightmare into a seasonal, waterborne delivery system. This was not fighting nature, it was synchronizing human ambition with the planet's own cycles. Perhaps no civilization exemplifies this environmental synergy more clearly than the Inca. Their empire was the mountains, and their engineering reflected that unity. Instead of carving straight roads through impassable peaks, they built suspension bridges from woven grass cables across dizzying gorges. Their trails switchbacked up slopes following the natural contours. Most tellingly, their architecture was designed for seismic survival. The flexible, interlocking joints of their polygonal walls allowed the stones to dance during an earthquake and then settle back into place, a design learned from millennia of observing how the land itself moved. Their buildings were not placed upon the landscape, they were born from it, their forms echoing the fractured, angular shapes of the surrounding Andes. This leads us to a pivotal question. How much did the local environment dictate the specific techniques we see? The evidence suggests it was the primary sculptor of method. You do not use freezing water to quarry in the tropics. You do not rely on seasonal river floods in a desert with no major river. The available materials, the climate, and the topography created a menu of possibilities, and each culture engineered brilliant solutions from that menu. This intimate partnership between builder and land inevitably infused the work with deeper meaning. The stone was not just a neutral material, it was a piece of the living world, chosen and shaped with a reverence that blurred the line between engineering and ceremony. This connection between the physical stone and the spiritual landscape suggests the final layer of our mystery may not be in the how, but in the why that resonates within the material itself. Stone was never just a building material, it was a sacred threshold. In the minds of the ancient builders, these massive blocks formed a bridge between the solid, enduring earth and the untouchable realm of the heavens. This spiritual dimension is the silent partner in our paradox, for the obsessive precision we see may have served a ritual purpose as much as a practical one. The flawless joint was not merely a feat of engineering, it was a seal ensuring the integrity of a cosmic vessel. Anthropologists studying animistic traditions note a widespread ancient belief that stones were alive, vessels for spirits or concentrated earth energy. A rock was not an inert object but a being with its own presence. This worldview fundamentally changes how we interpret the craftsmanship. Shaping such a stone was not an act of domination, but of respectful collaboration, a ceremony in itself. We can imagine rituals that might have accompanied the quarrying of a sacred block, perhaps blessings spoken before the first cut, or offerings left in the quarry pit once the stone was freed. The choice of location was equally charged. Quarries were not just convenient sources of rock, they were often sacred sites, chosen because the stone itself was believed to possess unique properties. This is vividly illustrated by the blue stones of Stonehenge. These distinctive spotted dolerite pillars were not sourced locally. They were hauled over 200 miles from the Preseli Hills in Wales, an unimaginable effort for a people without the wheel or metal tools. Why undertake such a journey when suitable stone was available closer? Archaeological consensus suggests the blue stones were chosen for their perceived magical or healing properties, their transport a pilgrim's progress that imbued the monument with power drawn directly from a distant, holy landscape. The stone's origin was part of its meaning. This symbolic layer forces a reflective question. Did the profound meaning behind these structures actually drive the development of the advanced methods? If a stone is the eternal home for a pharaoh's spirit or the anchor point for a celestial alignment, then close enough is a spiritual failure. The ritual necessity for perfection could have been the engine that pushed technological innovation to its absolute limits, funding generations of trial and error to achieve the flawless results the ceremony demanded. This intertwining of sacred purpose and technical mastery brings the paradox into sharp, human focus. It moves the mystery from the workshop into the temple, suggesting that the true blueprint was not just geometric but spiritual. And such profound, society-wide spiritual projects require a foundation far more tangible than faith alone. They demand a vast and organized economic engine to turn belief into stone. The sheer scale of these projects demanded a civilization in miniature, a temporary city devoted entirely to stone. Behind every megalith moved and every joint perfected stood not just artisans but a vast, humming economic engine. This engine was fueled by people, thousands of them, organized with a precision that rivals the stonework itself. To understand how the impossible was built, we must look past the quarries and temples to the sprawling worker settlements, the grain silos, and the complex systems of obligation that turned human effort into architectural wonder. The traditional image of whip-driven slaves hauling stones under the desert sun has been largely overturned by archaeology. Excavations around the Giza Plateau have revealed something far more fascinating: the remains of bakeries, fish processing areas, and dormitory-style housing. This was not a prison camp but a carefully managed project site. Historians like Mark Lehner, who excavated these bakeries, found evidence of an industrial-scale operation capable of producing thousands of loaves of bread daily. This points to a workforce that was housed, fed, and cared for by the state. The labor system behind this was likely a form of corvée labor, a rotational duty where citizens contributed their work as a form of tax or civic service, often during the Nile's inundation when farming was impossible. This was not slavery, but an expected contribution to a national project that reinforced social cohesion and divine order. In other cultures, the motivation may have been more directly spiritual. For the builders of European cathedrals in the medieval period, or for communities contributing to a local temple, the work was often an act of piety, a volunteer effort that earned spiritual merit. The common thread across these systems is organization. Mobilizing a workforce of 10 or 20,000 people for decades requires a bureaucracy capable of counting, recording, and allocating everything from rations of barley and beer to shipments of copper tools and abrasive sand. The logistics of daily life at a site like Giza were a monumental achievement in themselves. A permanent managerial class would have been needed, overseers who could translate the architect's geometric plans into daily tasks for work gangs. These gangs, some evidence suggests, even took prideful names like the Vigorous Gang or the Craftsman Gang, which were sometimes graffiti-ed onto stones they placed. Housing had to be constructed, not just barracks but also homes for administrators, priests, and skilled craftsmen. A steady supply chain had to bring food from estates across Egypt, fresh water from the Nile, and timber from Lebanon. Medical care was necessary as skeletons found in worker cemeteries show signs of healed fractures, suggesting they received treatment and were not simply discarded. This structured, hierarchical society within a society was the true scaffolding upon which the pyramids rose. It transformed raw human potential into a directed, sustained force. This brings us to a pivotal question. Could this sheer organizational prowess, this mastery of logistics and human resources, be the missing catalyst that explains the efficiency gap in our modern experiments? When we attempt to replicate an ancient technique today, we do so with a small team over a few weeks or months. The ancients operated with the power of a small city, working in shifts across generations. A technique that seems painfully slow in a one-off test becomes astonishingly productive when multiplied by 10,000 hands, day after day, year after year. The wear and tear that baffles us, the rapid degradation of copper saws or the consumption of abrasive sand, ceases to be a mystery when you have dedicated workshops constantly forging new tools and quarries endlessly producing fresh sand. The economic system was the engine that made the slow, meticulous methods not only possible but sustainable. It turned the patient, millimeter-by-millimeter progress of the individual into the rapid, mountain-building progress of the civilization. This relentless, organized effort, however, leaves its own signature not just in records but in the very materials. The stones themselves bear silent testimony to the passage of countless hands and the persistence of a collective will that shaped an era. The Great Pyramids of Giza stand as a timeless peak, yet that peak was not sustained. After the monumental frenzy of Egypt's Old Kingdom, the age of colossal stone pyramids gradually faded. Why would a society, having seemingly mastered the art of moving mountains, turn away from its greatest expression of power? The answer lies in a quiet truth about innovation. It is not a permanent ascent, but a series of peaks and valleys shaped by cost, culture, and sheer human endurance. Some of the most advanced stone-cutting techniques may not have been lost in a single cataclysm, but were simply abandoned, their immense practical demands outweighing their perceived benefits over time. This is the phenomenon of technological regression, where societies adapt or even step back from complexity when circumstances change. The pyramid's decline offers a clear case study. The organizational machine required to build one was staggering, consuming a vast portion of the state's wealth and labor for decades. As political power fragmented after the Old Kingdom, that centralized authority and resource pool evaporated. The knowledge of how to build a pyramid did not vanish overnight, but the unwavering collective will to do so certainly did. Future pharaohs, perhaps learning from the economic strain on their predecessors, opted for less extravagant, more secure tombs hidden in the Valley of the Kings, carved into the living rock itself. This was not a loss of skill, but a strategic adaptation, a shift from external monument to hidden fortress. The techniques for exquisite stonework lived on in temples and statues, but the specific societal engine for pyramid-scale projects fell idle. This pattern of knowledge fading is often tied to the fragility of how it was held. In a world before widespread literacy, the most nuanced secrets of a craft resided in oral tradition and muscle memory, passed from master to apprentice. If a guild was dispersed by war, if a generation failed to find dedicated students, or if a material became scarce, that chain could break irreparably. The collapse of empires, like the Bronze Age collapse around the Mediterranean, severed trade routes and scattered specialized artisans, causing regional technologies to regress or transform beyond recognition. Sometimes the method itself was its own undoing. A technique might be so labor-intensive, so dependent on a finite resource, that it became unsustainable. Imagine a polishing compound that required a rare mineral from a single, depleted quarry, or a transport method that consumed forests faster than they could regrow. When the cost, both in materials and human effort, grew too high, societies would innovate toward efficiency, even if the new method was, in absolute terms, less precise or less durable. We see this shift vividly in materials. Across the ancient world, as monumental stonework waned, baked mud brick became the dominant building material. It was faster, cheaper, and required far less specialized skill. This was a pragmatic choice, enabling rapid expansion and housing for growing populations. The Roman architectural revolution presents the ultimate example of this adaptive shift. While the Romans admired and incorporated Greek stone columns, their own empire was built on concrete. This revolutionary material, a mix of lime, volcanic ash, and rubble, could be poured into wooden molds, creating vast, curved spaces like the Pantheon's dome, structures that would have been inconceivable with cut stone. Concrete changed the architectural priority from precision assembly to fluid form. The focus moved from the painstaking craft of the joint to the sweeping genius of the vault. In many ways, it was a more advanced technology, but it made the old mastery of multi-ton stone fitting functionally obsolete for most large-scale projects. The stone-cutting techniques persisted, but in a narrower domain for elite temples, commemorative monuments, and decorative elements, no longer as the backbone of an empire's infrastructure. This historical ebb and flow forces a reflective question about our entire timeline. Are the pinnacles of ancient stonework we marvel at today not signposts on a steady upward climb, but isolated peaks in a rugged landscape of innovation? A culture might reach an extraordinary height of technical ability, fueled by a unique combination of religious fervor, political unity, and resource availability. When those conditions change, that specific knowledge can recede, preserved only in the silent stones it left behind, waiting for a future age to wonder at its method. This realization that history is not a straight line but a story of variable focus brings our investigation to its most practical frontier, to move from wondering about lost peaks to actually mapping their contours. We must turn to the meticulous, often dusty, work of modern discovery. Our historical puzzle is assembled from fragments that time did not destroy. This is the fundamental limitation of archaeology, a discipline built upon the enduring, while the tools of creation were often anything but. We marvel at the granite box, but the wooden sledges, the fiber ropes, the woven baskets full of abrasive sand, and the water skins have long since returned to the earth. Our picture of the past is not just incomplete, it is systematically biased toward the indestructible, leaving us to reconstruct the delicate, ingenious mechanisms of an entire civilization from the silent stones they left behind. This gap between the surviving result and the vanished process is where the stone-cutting paradox truly lies. As archaeologist and engineer denies Stocks, who dedicated his career to replicating ancient tools, once noted, the greatest challenge is that the very implements used to work hard stone were themselves soft and consumable. A copper saw, constantly worn down by abrasive sand, would be recycled until it vanished. A rope, frayed and broken, would be discarded without a trace. We are left interpreting the magnificent, permanent artifact while the ephemeral, yet critical, technology that created it has evaporated. This evidentiary void is compounded by several relentless forces. First, the simple perishing of organic materials. Wood, leather, plant fibers, and even certain softer stones used as tools simply decay over centuries, especially in humid climates or fluctuating environments. Second, natural erosion. Wind, water, and seismic activity can smooth away the most delicate tool marks, the very fingerprints of the craftsman, leaving surfaces that appear mysteriously pristine. Third, and perhaps most frustrating, is the human activity of later cultures. Sites were often reused, stones were quarried for new buildings, and ancient foundations were built over, creating a palimpsest where the original context is blurred or obliterated. A classic example of this is the ongoing debate surrounding the Sphinx enclosure at Giza. The weathering patterns on the limestone walls have led some geologists to propose a much older date for the sculpture, arguing that the erosion was caused by prolonged rainwater runoff in a period when the climate was wetter. Mainstream Egyptologists, however, point to the complex archaeological context of the site, the pottery finds, and the stylistic links to the Old Kingdom, advocating for the traditional timeline. This controversy underscores a core challenge. How do you definitively date a stone monument when the most telling evidence, the campfires of its builders or the chips from its carving, may have been swept away by millennia of desert winds or buried under later settlements? The profound impact of a single surviving artifact shows us just how much we might be missing. For over a century, the Antiquity mechanism, a corroded lump of bronze gears recovered from an ancient shipwreck, was considered an incomprehensible oddity. Only through advanced imaging techniques did researchers realize it was an astonishingly complex astronomical calculator, a device that could predict planetary positions and eclipses. This one object single-handedly revolutionized our view of Greek technological sophistication. It proved they possessed knowledge of gearing and precision, metalworking that historians never imagined from the textual record alone. It stands as a stark reminder, a time capsule whispering that our textbooks are written from the fraction of the past that stubbornly refused to disappear. So we must ask, what other Antiquity mechanisms are still hidden, not in shipwrecks but in the very fabric of sites we have studied for generations? Could the answers to the stone-cutting paradox lie not in a grand, undiscovered machine, but in the subtle residues of plant-based compounds on a quarry wall, or in the microscopic wear patterns on a common stone hammer that we have yet to analyze with the right technology? These inherent limitations force a crucial shift in methodology. They highlight why solving these ancient mysteries can no longer be the work of the archaeologist alone. It requires a convergence of disciplines, a dialogue between the trowel and the electron microscope. Geologists analyze stone sources and weathering. Materials scientists test the properties of ancient copper alloys. Engineers build load-bearing models to test transport theories. Chemists search for organic residues. This interdisciplinary approach is slowly building a bridge across the evidentiary gap. It turns the frustration of missing pieces into a focused search for new kinds of evidence, evidence that does not shout from a museum display case, but whispers from a soil sample or a laser scan. It acknowledges that the full story of the ancient builders is written not only in their monuments, but in the chemistry of their tools, the physics of their methods, and the very ecology of their worksites, a narrative we are only now learning how to read. A recent study focused not on the stones themselves, but on the whispers they left behind. Researchers employed high-resolution 3D scanning to map the microscopic topography of tool marks on an ancient Egyptian granite artifact. This digital fingerprint, invisible to the naked eye, revealed a consistent harmonic pattern in the cut, a signature that suggested the use of a rotating tool with a steady, machine-like feed rate. This finding did not emerge from an archaeology department alone, but from a collaboration between historians, materials scientists, and mechanical engineers. This is the new frontier, where the stone-cutting paradox is being dismantled piece by piece through a powerful convergence of disciplines. Geology, engineering, chemistry, and astronomy are no longer separate fields looking at the same mystery. They are merging into a single investigative force, each providing a unique lens on the past. The benefits of this collaborative spirit are profound, filling the evidentiary gaps that have long frustrated traditional archaeology. Chemical analysis of stone surfaces can now detect trace residues of organic compounds, testing the tantalizing theory of plant-based softening agents. Where pattern studies on surviving copper tools, examined under electron microscopes, tell a story of how they were used, the angle of attack, the type of abrasive, and the duration of work. Computer modeling allows engineers to simulate the physics of moving a 1,000-ton block, testing the efficiency of different ramp angles, lever systems, and team configurations in a virtual space before a single log is rolled in reality. This interdisciplinary approach transforms speculation into testable hypothesis. Perhaps the most public example of this convergence is the Scan Pyramids mission. An international team of physicists and archaeologists is using muon tomography, a technique that employs cosmic ray particles to see through solid stone, to explore the void spaces within the Great Pyramid. This is not treasure hunting, it is structural analysis on a cosmic scale. By mapping density variations, scientists hope to understand the internal architecture, the construction methods, and perhaps identify previously unknown chambers or stress-relieving features. The data they gather will be interpreted not just by Egyptologists, but by structural engineers who can read the pyramid skeleton, revealing how it has distributed its immense weight for 4.5 millennia. A beautiful illustration of how this works comes from a seemingly solved mystery on Easter Island. For years, the dominant theory was that the Moai statues were dragged horizontally on log rollers. Yet this never fully explained the oral traditions that said the statues walked. Then, a team incorporating archaeologists and soil scientists took a closer look at the landscape. They examined the ancient roads leading from the quarry. Instead of finding the deep, parallel ruts expected from sledges, they found a pathway of scattered, broken stone. The soil scientist recognized this pattern. It was the signature of something heavy being rocked or pivoted from side to side, fracturing the bedrock beneath. This physical evidence, interpreted through an environmental lens, gave credence to the walking theory and led to the successful replication experiments. The answer was always there in the dirt, waiting for the right pair of eyes to see it. This collaborative spirit prompts a reflective question. With this arsenal of modern science at our disposal, are we on the verge of finally cracking the ancient code? The tools we have today, from particle detectors to satellite imagery, allow us to ask questions of the past that were unimaginable a generation ago. We are no longer limited to what we can see. We can now probe for what is hidden, analyze what is invisible, and simulate what is lost. The paradox may not yield to a single eureka moment, but to a gradual, layered understanding built from 1 million data points. Each scan, each soil sample, each chemical assay adds another piece to the mosaic. This forward momentum, this sense of collective discovery, naturally turns our gaze from what we are learning now to what might still be waiting for us. If the present is defined by this fusion of science and history, what revelations might the next decade or the next century bring to light from the silent, enduring stone? The ocean floor holds more forgotten history than all the world's museums combined. This is the next frontier in our search for answers. A realm where rising sea levels at the end of the last ice age may have submerged the very workshops of lost civilizations. Underwater archaeology, once limited by depth and visibility, is now being revolutionized by robotic submersibles and high-definition sonar mapping. These tools allow researchers to scan vast areas of the continental shelf, searching for the geometric shapes of human construction beneath centuries of silt. Every anomalous structure, from the debated walls off the coast of Japan to the submerged circular formations in the Gulf of Cambay, represents a potential chapter in the human story that our current timeline cannot account for. The paradox is no longer a static puzzle from the past. It is a living, breathing field of inquiry where a single discovery tomorrow could rewrite the textbooks. This investigative spirit is pushing teams into the planet's most challenging environments. Dense, unexplored regions of the Amazon rainforest, long thought to be pristine wilderness, are now revealing their secrets from the air. Through the canopy-piercing eyes of LiDAR, laser scanning technology, archaeologists are discovering vast networks of ancient settlements, geometrically aligned earthworks, and complex road systems. These findings prove that sophisticated societies flourished in environments we assumed could not support them, forcing a complete reassessment of the scale and ingenuity of pre-Columbian cultures. Similarly, the melting ice sheets of Antarctica are a tantalizing, though highly speculative, frontier. While mainstream science firmly places the continent under ice for millions of years, the very possibility that ancient maps might hint at knowledge of ice-free coasts drives a compelling question. What if the slow retreat of glaciers reveals not just rock, but the hand of an unimaginably ancient human presence. The tools to analyze whatever we find are evolving just as rapidly. Artificial intelligence is being trained to recognize patterns invisible to the human eye. An AI can scan thousands of satellite images, identifying subtle topographic anomalies that suggest buried walls or plazas. It can analyze the wear patterns on 1 million stone tools, categorizing them by use and culture with superhuman speed and consistency. In the lab, advanced dating methods are pushing back the boundaries of time. Techniques like cosmogenic nuclide dating can now determine when a stone surface was first exposed to sunlight or carved, providing a direct date for a monument's construction that is independent of pottery or charcoal found nearby. This removes a layer of interpretive guesswork, allowing the stones to speak for themselves with newfound chronological clarity. The power of these converging technologies is best illustrated by a discovery that has already reshaped a continent's history. For centuries, the jungles of Cambodia were thought to have sporadically hosted the great temple of Angkor Wat. Then, archaeologists deployed airborne LiDAR over the landscape. The lasers penetrated the thick canopy, revealing the ground truth below. In an instant, the map transformed. They saw not an isolated temple complex, but a sprawling, low-density megacity the size of modern Los Angeles, with canals, highways, reservoirs, and hundreds of unknown temples. This was not a city hidden in the jungle, it was a jungle that had grown over a metropolis. The discovery proved the Khmer Empire was far larger, more populous, and more engineered than anyone had dreamed. It served as a humbling lesson. The most profound answers are often lying in plain sight, waiting for us to develop the right lens to see them. So what will we learn in the next decade? Perhaps a submersible will document a clearly artificial structure on the submerged Sunderland Shelf, a potential cradle of civilization now underwater. Maybe a new scanning technique will detect the chemical ghost of a plant-based softening agent on the joins at Sacsayhuamán, or an AI, sifting through global geological data, will identify a previously unknown source of an impossibly hard abrasive mineral traced back to an ancient trade route. The future of this mystery is not about finding a single silver bullet, but about connecting a galaxy of dots we are only beginning to perceive. This forward-looking perspective does not seek to end the conversation, but to open it wider, inviting us to see the ancient world not as a closed book, but as a story whose most thrilling chapters may still be waiting to be read. Our journey through the quarries and mountains leaves us not with a single answer, but with a profound appreciation for the tapestry of human ingenuity. The stone-cutting paradox, in the end, is less a locked door and more a mirror, reflecting the incredible diversity of paths our ancestors took to solve impossible problems. We have seen the millimeter-perfect geometry of Egypt, the earthquake-defying puzzles of Peru, and the logistical miracles of Baalbek. We have weighed the evidence for abrasives and chemistry, for levers and sound, for economic engines and sacred purpose. Each thread in this tapestry offers a possible explanation, yet the complete picture remains a testament to the boundless capacity of the human spirit when driven by collective belief. These mysteries do more than ask how stones were cut, they ask why we build at all. They speak to a universal drive to create permanence, to commune with the cosmos, and to leave a mark that whispers across millennia. This enigma invites us to a deeper humility. It asks us to look at the ancient world not as a primitive prelude to our own, but as a collection of unique peaks of knowledge, some of which we are still struggling to climb. The true lesson may be that history is not a straight line we have surpassed, but a vast landscape we are only beginning to map. So, what do you think? Does the evidence for patient, mastered skill with simple tools satisfy you, or does the scale and precision point to a forgotten chapter in our shared story? Share your perspective in the comments below. If unraveling these puzzles with us has sparked your curiosity, Subscribe to continue exploring the world's greatest historical mysteries together. Thank you for joining this investigation into the stones that should not exist. Keep questioning, keep wondering, and never stop looking for the extraordinary in the ancient world.